You know, in the world of artificial intelligence, it feels like we're living in a whirlwind. Every single day, sometimes every single hour, there's a new headline, a new model being released, a new feature that promises to completely change the game. It is a constant, relentless flood of information, and frankly, it can be really tough to keep up. It's even harder to sift through all that noise and figure out what is a genuine, fundamental leap forward versus what's just, good marketing or a minor little tweak. But every once in a while, something comes along that just cuts right through all of it. A development that is so foundational, so elegant in its solution to a core problem that it signals a true paradigm shift is underway. Today, we're going to dive deep into one of those very breakthroughs. This is a technology that takes aim at one of the single biggest, most expensive, most frustrating problems in all of AI. And the solution it offers doesn't just promise to make our AI models faster, it promises to make them significantly smarter, too.
So, to really wrap our heads around how significant this is, you have to understand where this news came from. This wasn't just a blog post or a press release. This technology was unveiled in a research paper that just won the Best Paper Award at ACL. Now, for anyone who isn't deep in this field, let me just put this in perspective. ACL stands for the Association for Computational Linguistics, and saying it's a big deal is the understatement of the year. This is the single most important, most prestigious, and most rigorous academic conference for natural language processing. That's the science of teaching computers to understand and use human language. This is the main event. It is the World Cup. It is the Super Bowl. It is the Olympics of this entire field, all rolled into one. The absolute titans of the industry, the brightest minds from academia and from the massive AI labs, all gather here to present their best work. This is the very same conference where the seeds of the modern AI revolution were planted. The groundbreaking Attention is All You Need paper, the one that introduced the transformer architecture that powers literally everything from ChatGPT to Gemini. That made its debut here. So when a paper is singled out from thousands of submissions and given the Best Paper Award at ACL, the entire industry, and I mean everyone, stops what they're doing and pays very, very close attention. The paper is called Native Sparse Attention. It's from a brilliant team at DeepSeek AI and Peking University. And the ideas inside, well, they're about to change everything.
Okay, so before we can pop the champagne and celebrate this incredible new solution, we first have to get our hands dirty and really understand the problem it's solving. Because this isn't some small niche issue. This is a fundamental bottleneck. It's a flaw that is baked into the very DNA of almost every single large language model that we use today. To appreciate the genius of the solution, we have to understand the adversary. We have to get to grips with what I'm calling AI's attention problem.
This quote right here, this comes directly from the paper itself. It's one of the first things the authors say, and it lays out the problem so clearly. Let's break it down. The high computational cost. What does that really mean? It means time, it means electricity, it means expensive, specialized computer chips running at full tilt. It's the brute force, the raw energy required to make the AI think. And what's causing this cost? The standard attention mechanisms. This is the core process that allows an AI to understand context. And the authors state plainly that this cost creates significant computational challenges. Now, challenges is a very polite academic way of putting it. What this really means is a massive, expensive, progress-halting wall. This is the reason why trying to get an AI to analyze a really long document, like a 100-page legal contract, can take forever or cost a small fortune. It's the hidden friction that has put a practical ceiling on the complexity of the problems we can throw at our best AI models. If you've ever sat there watching the cursor blink, waiting for an AI to finish writing a long email or a report, you have personally felt the effects of this exact problem.
So what is this standard attention that's causing all the trouble? It's a specific method called full attention. And to really get it, let's use an analogy. I want you to imagine a student. This student is incredibly diligent, incredibly dedicated. They have a perfect, flawless photographic memory. Sounds great, right? Well, here's the catch. They are also deeply, profoundly inefficient. Here's how they work. Every single time the teacher says a new word, just one new word, in order to understand its meaning in that sentence, this student mentally rereads the entire textbook from page 1 all the way up to the current sentence. They compare that one new word to every single word that has ever been said or written in that class. That, in a nutshell, is full attention. Now, if the class is just starting and the textbook is only 5 pages long, okay, it's manageable. But what happens when we're talking about a 500-page novel or a whole library of books? The amount of work explodes. It gets worse and worse, growing quadratically. That's a fancy way of saying that if the length of the text doubles, the amount of work required to process it doesn't just double, it quadruples. This is the exact opposite of how a smart human reads. When we read, we skim. We get the gist, we build a mental map. And if we need to find a specific detail, we don't start back at page 1. We know instinctively where to look. We focus our attention only on what's relevant. For years, the core problem has been that our AIs have been built like that inefficient student, not like an efficient human reader.
And the result of this deeply inefficient process isn't just a theoretical problem for computer scientists. It has a painful, practical, real-world impact. It creates this massive computational bottleneck. This is why you might hear a company announce that their AI has a 1 million token context window, which sounds amazing, but in reality, the effective length the model can handle without slowing down to a crawl or becoming astronomically expensive is often much, much smaller. This inefficiency is like a ball and chain that we have shackled to the ankle of every large language model. It's what's holding the entire field back from tackling the really massive-scale text analysis problems. Things like understanding an entire software code base with millions of lines of code, or reviewing a full set of legal discovery documents in a huge case, or analyzing a person's entire lifetime of medical records to find patterns. We couldn't do it. The cost and the time were just too high.
And if you want to know just how big that ball and chain is, look at this number. This comes straight from the research paper. For long documents, this one single inefficient process, this full attention, can account for 70 to 80% of the total computation time. Let's really let that sink in. Imagine, for every $10 you spend running these powerful AI models, up to 8 of those dollars are being burned by this one bottleneck. For every hour you wait for a result, nearly 50 minutes of that is the AI just spinning its wheels, rereading everything over and over again. It's an immense waste of energy, of processing power, of money, and of time. Solving this wouldn't just be a small improvement. It would be a complete revolution in the economics and capability of AI.
So if the problem is that our AI reads like an inefficient brute force machine, it seems logical that the solution is to teach it to read more like a person. And that is exactly where the story takes a turn. This is where our hero technology enters the scene. It's the core idea behind this award-winning paper. It's called Native Sparse Attention, or NSA for short. And it is a fundamental redesign, a rethinking of how AI should pay attention, moving it away from brute force and towards something that looks a lot more like intelligent focus.
All right, let's look closely at this definition because the words here are chosen very carefully. First, native. This word is absolutely crucial. It means this new, efficient way of reading isn't a patch or an afterthought. It's not something bolted on at the end. It means the AI learns this skill from the very beginning of its training, from day one. It's woven into its very digital fabric. Second, sparse. This is the opposite of full or dense. Instead of looking at every single word, the AI learns to ignore the vast majority of the text that's irrelevant noise. It learns to focus its attention sparsely, only on the most critical pieces of information needed for the task at hand. And the result of these two things working together? A dramatic, almost unbelievable increase in both speed and efficiency, without losing the crucial information that actually matters.
So the big question is, how does it actually work? How do you teach a bunch of code to read like a human? Well, NSA uses this brilliant 3-part strategy that mimics our own reading habits. First, it learns to skim for the big picture. For text that is way back in the document, say in the early chapters, NSA doesn't bother storing every single word. Instead, it creates these compact, compressed summaries of those text blocks. Think of it like reading the cliff notes for the early parts of a book, to get the global context, the main plot points, without getting bogged down in every adjective. Second, it learns to pinpoint the important details. This is the search function. Based on what it's currently thinking about, NSA uses that high-level summary to intelligently select only the most relevant original text blocks to go back and reread in full detail. So if you ask a question about a character who was introduced in Chapter 3, the AI doesn't reread the whole book. It knows to jump right back to Chapter 3 and focus its full attention there. And third, it learns to remember what just happened. NSA keeps a high-fidelity, full-attention focus on the most recent sentences. It knows that what was just said is often the most critical context for what is being said right now. It keeps that short-term memory crystal clear.
Now, this diagram from the paper might look a little complicated, but it's basically the blueprint for this smart reader we've been talking about. You can see those three strategies right there. The compression part handles the global summary, the cliff notes. The selection part is what pinpoints those specific details from the past, and the sliding window keeps a close eye on the most recent text. But the real genius, the secret sauce, is that little box at the bottom, the gated output. You can think of this as a smart controller or a conductor. The AI learns how to use this gate to dynamically decide how much weight to give each of those three strategies at any given millisecond. Is the global summary the most important thing right now, or does it need a specific detail from way back in Chapter 1, or is the most important thing the sentence that just came before? This gate learns to mix and blend these three information sources together in the perfect ratio to achieve the best possible understanding moment by moment. It's a dynamic, intelligent system, not a rigid, fixed one.
And we come back to that all-important word, native. What makes this approach a true breakthrough, and not just another interesting idea, is that it's natively trainable. Many researchers have tried to create sparse attention before, but most of those attempts were like trying to perform a heart transplant on a car. You take a fully trained AI model, and then you try to bolt on this new sparse attention mechanism at the end. And sure, it could kind of work, but it was always awkward, it was inefficient, and it almost always hurt the model's performance. NSA is completely different. The model is trained from scratch with this sparse mechanism built in. It learns from the very first moment of its existence how to efficiently allocate its attention. The sparse mechanism and the rest of the model's brain grow up together. They learn together, and they optimize themselves in perfect harmony. It's a native speaker of this new, efficient language.
Okay, so the theory is beautiful. It's elegant. An AI that mimics our own reading strategies, built from the ground up to be incredibly efficient. It just makes sense. But the billion-dollar question is, does it actually work in the real world? This is where we move from theory to proof. The performance data that the researchers published in the paper is, and I'm not exaggerating, absolutely staggering. This is where we see the undeniable evidence that this new method is not just faster, it's also smarter and just plain better.
Let's break down these charts, because they tell the whole story. On the left, we're looking at performance, how well the AI performs on a range of tasks. The orange bar is the old way, the baseline, full attention model. The red bar is our new NSA model. Now look closely. The red bar isn't just matching the orange bar. In every single case, it is slightly higher. This is the holy grail. You're not making a trade-off. You're not sacrificing quality to get more speed. You're getting better quality and more speed. It's a pure win-win. Now look at the chart on the right. This one is all about speed. The orange baseline is set to 1x. The red bars show the speed up you get with NSA. And just look at that last bar, in the decode phase. That's when the AI is actually generating its response. The speed up is a massive 11.6 times faster. This isn't a 10% improvement. It's a game-changing, revolutionary leap in performance.
Let's just pause on that number for a second. 11.6 times faster. This isn't a minor tweak. It's not a small optimization. This is a leap of an entire order of magnitude. What this means in practice is that an analysis that used to take a full minute to run could now be finished in about 5 seconds. A task that used to take an hour is now done in 5 minutes. This kind of speed completely transforms how we can interact with AI, turning long, drawn-out analytical tasks into something that feels nearly instantaneous.
But remember, it's not just faster, it's also smarter. This table gives us a much more detailed look at the performance, and I want you to focus on those last two columns. Reasoning. GSM 8K and DROP are benchmark tests that are designed to be incredibly difficult. They measure things like multi-step mathematical and logical reasoning. They're designed to trip AI up. Now, with the old full attention model, the scores were pretty good. You can see them there. But now look at the scores for the NSA model, in bold. In every case, the scores jump up significantly. This is clear proof of an improvement on the very tasks that require deep, complex, logical thinking.
This leads to a really fascinating and almost counterintuitive insight. Why does forcing the AI to do less work by ignoring information actually make it smarter? The researchers have a great theory about this. The old model, the one with full attention, was being force-fed every single word, whether it was relevant or not. Imagine trying to solve a complex calculus problem while 1,000 different radio stations are blaring random words at you all at once. It's overwhelming. It's just noise. The new NSA model,
by its very design, learns to filter out all of that irrelevant noise. It learns to tune out the distracting radio stations and focus only on the information that has a high signal. And in that focused, quiet environment, it can actually think more clearly. By cutting out all the distractions, its core reasoning ability actually gets better.
But this raises a critical question. If you're summarizing and selecting and ignoring parts of the text, don't you risk missing that one tiny but absolutely crucial fact, that one needle in the haystack? Well, the researchers tested exactly that. They used a famous benchmark called the needle in a haystack test. It's simple. They hide one unique specific sentence, the needle, somewhere inside a massive document. In this case, 80,000 words long. Then they simply ask the AI to find it and repeat it back. This chart shows the results of that test. The grid represents the entire document broken into chunks, and that solid green color you see across the entire grid means one thing: perfect, 100% accuracy. It didn't matter where they hid the needle, at the beginning, in the middle, or near the end. NSA's intelligent reading strategy found it perfectly, every single time. This is the definitive proof that its smart, efficient approach doesn't sacrifice precision one bit.
So, let's connect all these dots. We have a technology that is dramatically faster, significantly cheaper to run, demonstrably smarter at complex reasoning, and just as accurate at finding tiny details. When you put all of that together, you realize this isn't just another incremental update. This is a foundational shift in the underlying mechanics of artificial intelligence. So what does this mean for the future of AI? And maybe more importantly, what does it mean for all of us who are going to be using these tools?
The real-world implications here are just enormous, and they're going to happen on several levels. On the surface, the first thing we'll all feel is just faster responses from chatbots and other AI assistants. Less waiting, more doing. But the bigger impact is economic. By making the core computation over 10 times more efficient, the cost of running these massive models is going to plummet. This makes powerful AI services cheaper, more accessible, and allows them to be deployed in many more places. But the most exciting changes are in the sheer scale of the problems we can now tackle. We can finally move beyond analyzing single articles or reports and start thinking about analyzing entire books or entire series of books all at once. Imagine a financial analyst feeding an AI a company's last 20 years of annual reports and shareholder calls and getting deep, nuanced insights back in seconds. Imagine a software developer giving an AI an entire, complex, multi-million-line codebase and asking it to find bugs or explain how it works. The barrier to understanding truly massive amounts of text is being demolished right before our eyes.
And perhaps the most critical, most exciting takeaway is this direct quote from a third-party analysis of the paper. This is not some far-off theoretical dream. This is not a science experiment that might be practical in 2035. The researchers who built NSA were not just academics, they were engineers. They specifically designed this system to run efficiently on the exact same chips that power today's AI data centers. They state that it is a ready-to-deploy system module. This is a practical, validated, powerful piece of engineering that we can and should expect to see integrated into the next generation of large language models, probably very, very soon.
And so, we end on this question, which I think is the most important one of all. For the entire history of computing, our primary limitation has been technological. We simply couldn't process information fast enough. That barrier is now crumbling. The bottleneck is shifting away from the machine's ability to read and toward our ability to ask good, meaningful, insightful questions. When you have an assistant that has read every single medical journal ever published, what is the right question to ask it to help find a cure for a disease? When it has read every legal precedent and every law book, what is the right question to ask it to help build a more just and fair society? The technical challenge is being solved. The next great challenge, the next frontier, is one of human curiosity and human imagination. The era of the hyperliterate, super-fast AI is here, and we're just at the very beginning of figuring out what to do with it.